So, imagine you have a state-of-the-art freezer, like an absolute top-of-the-line, beautiful, highly engineered machine.
Okay, I am picturing it.
And it is designed specifically to keep your absolute favorite ice cream just flawlessly chilled.
Right. Sounds perfect.
Yeah, but now take that image and just dial it up to 11.
Oh, wow.
Because instead of ice cream, you need to cool down a highly sensitive quantum computer or, a deep space sensor. And you need to cool it to almost absolute zero.
Right, which is, I mean, we are talking about fractions of a single degree above the point where all atomic movement literally stopped.
Exactly.
And, just to set the stakes for you, the listener, right away, building this freezer isn't just a fun theoretical physics exercise.
No, definitely not.
It is currently a massive global emergency. Right now, to reach those ultra-low temperatures for our most advanced technologies, well, the weight relies almost entirely on a specific, incredibly rare isotope.
Helium-3.
Exactly, helium-3.
Which, if I remember correctly, is basically a byproduct of the radioactive decay inside nuclear warheads. Like, it's not something we can just synthesize in a high school chemistry lab.
Far from it, yeah. Helium-3 is staggeringly expensive, and we are facing these severe, compounding global shortages.
So it's a huge bottleneck.
Right. We're practically running out of the very coolant required to run the next generation of human technology. So scientists have been desperately trying to build a new kind of freezer.
A solid-state refrigerator, essentially.
Exactly. One that just doesn't need helium-3 at all.
But here's the catch. The only material scientists thought they were allowed to use to build the internal components of this microscopic freezer. It is basically the equivalent of a thick, heavy, down-filled winter coat.
Yeah, a material specifically known for trapping heat.
Right. It sounds like an engineering nightmare.
It really does.
You are trying to build the ultimate chiller out of something that physically refuses to let heat travel through it.
Yeah, which makes no sense at first glance.
Exactly. So welcome to the Deep Dive Lab. Today's mission is unpacking that exact paradox.
It's a fascinating one.
It really is. We are looking at a brand new, highly anticipated research paper. It was just published in the journal Nature, and it centers on this really strange question.
Which is, how do you build a microscopic freezer when your best cooling material creates a total traffic jam for heat?
Right. And the scientific community has just discovered an answer that, honestly, completely rewrites the rulebook.
It really does. They have synthesized a paradoxical material that completely solves this bottleneck.
It's amazing. But to really appreciate the magnitude of this discovery, we have to look at the wall scientists have been banging their heads against for decades.
Yeah, we should probably start with the cooling process itself.
Right. Because we are trying to reach sub-Kelvin temperatures, literally fractions of a degree above absolute zero.
And obviously, you can't just plug in a mini fridge to do that.
No, definitely not.
The process scientists use is called adiabatic demagnetization refrigeration.
That is a mouthful. Let's just call it ADR.
ADR works. And ADR is actually a beautiful piece of physics, really.
How so?
Well, instead of using chemical refrigerants pumping through tubes, ADR uses magnetic fields to pull heat out of a system.
Okay, let me try to visualize this for a second. If heat is just, atoms jiggling around, ADR is it like a magnetic sponge?
It's a magnetic sponge.
Yeah, like you squeeze it with the magnet and the heat drips out?
Actually, a sponge is a really good starting point.
Huh.
But let's look at what the atoms are actually doing in there.
Okay.
Imagine the atoms in a material are a bunch of tiny compass needles.
Okay, I can picture that.
Normally, they're pointing in all sorts of random directions.
Yeah.
And that chaos, that randomness, is a form of entropy.
Yeah.
And it holds heat energy.
Right. Chaos equals heat.
Exactly. Now, if you turn on a massive, powerful magnetic field, you force all those tiny compass needles to just snap to attention. They line up perfectly.
Okay, so the chaos is gone. The entropy just drops.
Yes. And because total energy has to go somewhere, that forced order literally pushes the heat energy out into the surrounding environment.
I see. Then you thermally isolate your material and you turn the magnetic field off.
And without the magnet, the compass needles want to go back to being random and chaotic.
Right. But to return to that chaotic state, they need energy. They need heat.
Oh, wow.
So they aggressively absorb the ambient heat from whatever they are touching, like, say, your quantum computer chip.
And the temperature of that chip just plummets.
Exactly.
Okay, that makes physical sense.
Yeah.
So why the winter coat analogy earlier? Like, why are we stuck with materials that trap heat.
Well, historically, the absolute best materials for holding all that magnetic entropy were magnetic insulators.
Insulators.
Right. Materials like one called NBCP. They have this amazing capacity to absorb heat because their atoms have a very high spin quantum number.
Spin quantum number. Let's translate that for a second. A high spin number basically means there are more ways for the atom to be chaotic, right?
In plain English, yes, absolutely. A higher spin number like S equals 7/2 in some of these atoms means there are far more possible magnetic microstates. And more microstates equals a bigger sponge.
Yes. A massive internal capacity to absorb heat. You have an enormous sponge.
Yeah.
But here is the fatal flaw.
They're insulators.
Exactly. Because they are insulators, they are physically terrible at conducting heat.
Because they don't have, like, free-flowing electrons to carry the kinetic energy around.
Precisely. In physics, we say their thermal conductivity scales down proportionally to the temperature cubed. We call that T-cubed scaling.
T-cubed scaling. Okay, I want to make sure I'm really grasping the reality of that math.
Sure.
If it's scaling to the temperature cube, that means as the temperature drops, the material's ability to carry heat doesn't just gradually slow down.
No, not at all.
It functionally collapses in on itself.
It drops off a cliff. The pipe carrying the heat gets exponentially narrower the colder it gets. Wow. So you have this amazing cooling potential locked inside the material, but you physically cannot pull the heat from the quantum computer into the material fast enough.
The heat literally gets trapped in a traffic jam.
Exactly. A total traffic jam.
So the obvious question then, for anyone listening, is why not just use a metal?
Right, because metals are phenomenal conductors.
Yeah. If you touch a piece of metal in a cold room, it feels freezing.
Okay.
Because it's pulling the heat out of your hand on like a multi-lane highway. The math there is linear, right?
It's linear. Yeah.
The highway stays open even when it's freezing.
It does. And scientists desperately wanted to use metals.
Mm.
But there was a massive theoretical roadblock.
What was it?
Well, to get that extreme cooling effect, you need those magnetic spins, those delicate compass needles, to exist in a very fragile, highly frustrated quantum state.
Yeah.
And for decades, the assumption was that if you put those delicate spins inside a metal, the sea of highly conductive, chaotic electrons rushing around would just completely destroy the fragile quantum states.
Oh, I see. It's like trying to build a delicate house of cards in the middle of a bustling, crowded interstate highway.
That is a perfect analogy.
The cards, which are the electrons, would just constantly be slamming into the table and knocking the cards down.
Right. Through scattering and interference, you could have the delicate quantum cooling sponge, or you could have the metal heat highway.
But you couldn't have both.
You couldn't have both. Until this paper.
Right. Let's look at this breakthrough study. It was published in Nature in February 2026.
Yes.
And the lead authors are Dr. Mingfang Xu, Dr. Shitong Zhu, and their colleagues from the Chinese Academy of Sciences, along with a few partner institutions.
And what they managed to synthesize is a rare earth intermetallic compound called EuCo₂Al₉.
That is another mouthful. Let's just call it ECA for our sanity.
Good idea. Let's stick with ECA.
So ECA, and they grew these as physical, shiny, centimeter-sized crystals in a lab.
They did. And what they discovered when they tested this ECA is really the massive twist of our deep dive today.
I love a good twist.
They found that ECA is a metallic spin supersolid.
Wait. A metallic spin supersolid. Okay, I know what a solid is. I know what a liquid is. And a metal. What on earth is a spin supersolid?
It is honestly one of the most beautiful paradoxes in quantum physics.
Okay, I'm listening.
A supersolid is a phase of matter that does two things at the exact same time that absolutely shouldn't happen together.
Which are?
It possesses the rigid, orderly, crystalline structure of a solid, and it possesses the frictionless, zero-resistance flow of a superfluid.
At the same time.
At the exact same time.
I'm trying to picture this. Is it like a synchronized swimming routine?
How do you mean?
Like the swimmers are frozen rigidly in their specific lanes. They aren't leaving their physical spots, but the wave of their movement travels through the entire pool with absolutely zero resistance.
That analogy actually works perfectly for the magnetic poles, the spins of the atoms.
Oh, really?
Yeah. The swimmers are the magnetic spins, and they are locked in a rigid lattice. They don't move.
Right.
But the magnetic energy, the excitations, or what physicists call magyons, they flow through those locked spins, completely frictionless.
Wow.
That is a spin supersolid. And up until this paper, we had only ever seen this bizarre state in those pesky insulators.
Oh. So seeing it survive and actually thrive inside a highly conductive metal like ECA is, like an unprecedented leap.
It really is. It's building the house of cards on the highway, and the cars are somehow leaving it perfectly intact.
That is wild. But how do you even prove something like that? It's not like you can put a quantum wave under a standard optical microscope.
No, you can't. You have to get incredibly creative.
So what did they do?
First, they needed to prove the solid part, that the spins were indeed locked in a rigid pattern.
Right.
So they used a technique called neutron diffraction at the ISIS facility in the UK and J-Park in Japan.
Wait. If they're shooting neutrons, neutrons are neutrally charged, right?
Right.
So how does a neutral particle interact with a magnetic field to show you the spins?
Good catch. They don't have an electric charge, but neutrons do have a magnetic moment.
Oh, I see.
Think of them as carrying a tiny internal compass.
Okay.
So they cooled the ECA down to 0.3 Kelvin, which is incredibly cold, and fired a beam of neutrons at the crystal.
And then what happened?
As the neutrons bounced off the europium atoms in the crystal, their internal compasses interacted with the magnetic spins of the material.
So by tracking how the neutrons scatter, you basically get a 3D topographical map of the magnetic forces inside the crystal?
Precisely. And what they mapped was this bizarre Y-shaped spin structure.
Y-shape.
Yes. The europium ions, which carry the heavy magnetic moment, they are arranged in a 3D stacked triangular lattice.
Okay.
And their spins were locked in this rigid Y formation, which definitively proved that the solid crystalline part of the supersolid state was intact.
Okay, so the synchronized swimmers are firmly in their lanes.
Exactly.
But how did they prove the frictionless wave part, the superfluidity?
For that, they used the metal's own properties to their advantage. They measured electrical transport and specific heat.
I'm not sure I follow.
Essentially, they used the conduction electrons, the cars on the highway, as tiny little spies.
Oh, I like that. Electron spies. But how does an electron spy on a magnetic wave?
Well, as the electrons flowed through the material, they would scatter off the local magnetic spins.
Okay.
By measuring the minute changes in electrical resistance, the scientists could sense exactly when the magnetic transitions were happening.
They could basically feel the waves.
Exactly. They found very clear transition points, like one at 3.6 Kelvin, which they labeled TN1.
Let's unpack TN1 for a second. What does that physical transition actually look like?
It's called the Neal temperature. It's the exact freezing point where the chaotic random magnetic spins suddenly snap into an ordered alternating pattern, an antiferromagnetic state.
Okay.
By tracking these transition temperatures with the electron spies, they created a perfect map of the internal quantum states, proving the superfluid wave definitely existed.
Okay, but this brings us back to the biggest mystery, doesn't it?
Which one?
If conduction electrons are literally slamming into these delicate magnetic structures to act as spies, how is this house of cards not collapsing?
Right.
Like, what is physically preventing the chaotic electrons from destroying the delicate quantum state?
This is where we get into the pure genius of the material itself. It all comes down to a mechanism called the RKKY interaction.
RKKY. Sounds like an old radio station.
It does, but it actually stands for Ruderman, Kittel, Kasuya, and Ucida, the four physicists who discovered it.
Ah, okay.
Remember those europium atoms making up the lattice?
Yeah, the ones arranged in the triangles.
Right. Well, the parts of them that act as the magnetic compass needles are these 4f electrons tucked deep, deep inside the atom's core.
Oh, so they aren't on the outside.
No. Yeah. They are physically too far apart to interact with each other directly.
So if they can't touch, they need a middleman to coordinate the synchronized swimming.
Exactly. And the middlemen are the conduction electrons.
Wait, really? The chaotic cars on the highway?
Yes. An outer electron zooms past one europium atom. Its own tiny magnetic field gets tweaked or polarized by that deep 4f electron.
Okay.
As that conduction electron keeps zooming along, it carries that specific magnetic tilt to the next europium atom, effectively passing the message along.
Oh, wow. So it's not a house of cards on a highway at all.
No, it's not.
The cars on the highway are acting like a massive high-speed game of telephone, constantly coordinating the structural integrity of the house of cards.
That is a much, much better way to look at it. The RKKY interaction, combined with the physical shape of the magnetic fields interacting what we call strong magnetic dipolar interactions, it stabilizes the whole system.
The very thing we thought would break the system is actively holding it together.
Exactly. It's brilliant.
That is just wild. But I was reading ahead in the notes, and there's a part of this experiment where the math completely failed them.
Oh, yes.
Something called the quantum meltdown. What
Yeah.
exactly melted?
This is perhaps the most fascinating anomaly in the entire study.
Oh, really?
Yeah, the classical physics models the standard traditional math we use to predict how these magnets should act well. It predicted something very specific.
What was that?
It predicted that when the scientists increased the external magnetic field to a certain point, there would be a sharp, sudden structural jump in the magnetization.
A jump from what to what?
From one rigid phase, called the UDD plateau, to another phase called the MSV state.
Okay, let's translate the alphabet soup really quickly. UUD stands for up, up, down, right?
Yes. Picture 3 magnetic atoms in a triangle. 2 point north, 1 point south.
Okay, so it's a very rigid, locked-in pattern. And the MSV start.
The MSV state is a phase where those spins start tilting or canting sideways. Now, classical math dictated that the transition between these two states should be like flipping a light switch.
Just a sudden snap.
A rigid snap from up, up, down, directly to tilted.
But I'm guessing it didn't snap.
It definitely did not.
Yeah.
When they actually ran the experiment, there was no sharp jump at all.
Bro.
It was a smooth, continuous curving change.
But why? If the math said it should snap, why did it bend? Are the electrons interfering again?
In a way, yes. The classical models completely failed to account for the sheer disruptive power of quantum fluctuations.
Oh,
The conduction electrons in the ECA were essentially supercharging the quantum chaos at a microscopic level.
so instead of a rigid classical snap.
That chaos caused the rigid order to just melt away into a smooth quantum transition.
Hence the quantum meltdown.
Exactly. It's a massive signature that this material isn't just behaving like a normal magnet.
Right.
It's governed entirely by deep, complex quantum mechanics surviving in a metal.
Okay, so we have this incredible metallic spin, super solid.
We do.
We have electron messengers playing a high-speed game of telephone to hold it together, and a quantum meltdown smoothing out the rough edges.
It's beautiful, elegant physics.
It really is. But let's zoom back out for you, the listener. We started this deep dive talking about a massive global shortage of helium-3.
We did.
Does ECA actually solve that problem, or is this just a really cool lab trick?
It absolutely solves the problem.
Really?
Yes. Let's look at the real-world numbers Dr. Hsu and Dr. Hsu reported.
Hit me.
This ECA material can cool things down to an ultra-low 106 millikelvin.
Wow.
And if they dope the crystal with a little bit of strontium, they can push it even lower, down to 80 millikelvin.
Which is astonishingly cold.
Yeah.
But, I mean, we knew insulators could get cold. The issue was the heat traffic jam.
Right. And here's the kicker. The thermal conductivity.
Okay.
At 100 millikelvin, the heat flowing through ECA is around 100 milliwatts per Kelvin meter.
Okay, give me the context for that number. How does 100 milliwatts compare to the old winter coat insulators like MBCP?
It is 2 full orders of magnitude better.
2 orders of magnitude.
Yes. The heat highway in ECA is 100 times wider and faster than the previous best insulator coolants.
That is insane.
Because the europium atoms have that high-spin quantum number of 7/2, you still have the giant sponge.
Right.
But because it's a metal, you finally have the fire hose to fill it up.
So if I am putting all these pieces together,
Yeah.
instead of relying on a staggeringly expensive depleting nuclear isotope to cool down our deep space sensors and quantum computers,
Yes.
this paper is proving that we can literally just grow these metallic ECA crystals in a lab and use them as solid-state, helium-free superchillers.
That is exactly the takeaway.
Yeah.
This material is a highly viable, scalable alternative to the helium-3 bottleneck.
That is huge.
It means we aren't going to hit a wall in developing commercial quantum computing or advanced space exploration just because we ran out of a rare gas.
The implications for the future of technology are just immense.
They really are.
That is just phenomenal. Okay, we have covered a massive amount of ground today. Let's synthesize the key takeaways for you.
Sounds good.
Number 1, scientists have successfully solved the winter coat paradox. They merged the massive cooling power of a quantum spin supersolid with the high-speed heat-conducting highway of a metal.
Right. Creating material that both holds heat and moves it incredibly fast.
Exactly. And number 2, the discovery of this ECA compound proves that delicate, chaotic quantum paradoxes can actually survive and even thrive inside 3D metals.
Because the conduction electrons don't destroy the delicate state. They act as messengers, using the RKKY interaction to coordinate the structure and hold it all together.
Exactly. And number three, the real-world payoff. This material provides a highly scalable, solid-state alternative to the severe global helium-3 shortage.
It really clears the path for better, faster, and more sustainable quantum computers without relying on rare nuclear byproducts.
If I can offer a final thought on the big picture here,
Please do.
what stands out to me is how human understanding actually progresses. We often think of scientific progress as inventive. Or often, the biggest leaps happen when we are forced to take two seemingly contradictory concepts like chaotic quantum spin fluctuations and orderly flowing metallic conductivity.
And we look hard enough to find the hidden mechanism making them work together in perfect harmony.
Exactly. The contradiction wasn't a wall, it was a door.
The contradiction was the door. I love that.
Yeah. And it leaves us with something really profound to think about. If this discovery is just the beginning, if we can engineer paradoxical metallic spin supersolids to freeze our most advanced computers, what other impossible quantum paradoxes might scientists uncover hiding in plain sight inside the everyday metals all around us?
That is a great question.
The metal in your phone, your car, your desk. What quantum secrets are still waiting for the right electron messenger to show us they exist?
It's exciting to think about.
It really is. Thank you so much for joining us in the Deep Dive Lab today. If you enjoyed unpacking this mystery with us, please follow and subscribe for more fascinating science stories. We will see you next time.